First of all, thank you for accepting the talk to this year paper. I'm Giulia Ventagli. I'm a PhD student at the University of Nottingham, and I will present the work published in a paper last November in collaboration with Yorgos Antonio, who will talk this afternoon, Antoine Lebel, and my PhD supervisor, Thomas Sotirio. I will talk about spontaneous scalarization in neutron stars for a theory that contains both the Gauss-Bonnet and the Ricci scalar couplings. So first of all, let me explain you what spontaneous scalarization is. It can be understood as a screening mechanism that allows a compact object, so a neutron stars or black holes, to have a non-trivial scalar configuration close to the compact object or inside the compact object where the gravity is strong. And at the same time, it allows to retrieve GR solutions far away from the compact object. So the theory that is affected by spontaneous scalarization effectively has two branches of solutions. And so the AGR branches of solutions and the scalarized branch of solution. And the transition between the two branches happens when a certain threshold is crossed. And usually it's a threshold is in compactness or in curvature. And spontaneous scalarization is particularly interesting because it allows to possibly discover new interesting physics in regional state of the space-time that so far have not been really searched for, so where gravity is strong, and at the same time it is in agreement with current observation where gravity is weak. It is inherently a non-perturbative mechanism, but it can be better understood if one performs a perturbative analysis of the phenomenon. So at a linear level, it is triggered by tachyonic instability. So here we have a Klein-Gordon scalar field equation. And if the scalar field acquires a negative effective mass square, then the scalar field exponentially grows. And this growth can be quenched if one takes into consideration the nonlinearity of the system. And if this happens, then we are left with a stable configuration of the scalar field around the neutron stars or the black holes. In our work, we studied this particular phenomenon for the theory that here I'm showing, which is the result of a previous work that we did in our research group. And this theory contains all of the terms that can trigger a tachyonic instability so that at a linear level triggers spontaneous scalarization. So we have a coupling between the Ricci scalar and the scalar field with the coupling parameter beta. And we have a coupling with the Gauss-Bonnet invariant, which its form is expressed here, coupled to the scalar field, and its coupling parameter is alpha. In principle, there could also be, we could also include a bare mass of the scalar field. We did not do so in our paper because it's clear that if we just include a positive bare mass of the scalar field, this will simply render GR solutions more stable. And it effectively renders spontaneous scalarization more difficult to achieve. In principle, there could also be a non-standard kinetic term here, but we are not including it because we showed in previous papers that this does not really affect the threshold of scalarization per se. So what we did is we studied this theory and we studied the full system of field equations, so the modified Einstein equation, which I'm not reporting here because it's quite complicated, and the scalar field equation here, where the effective mass square is the following. We studied this system for static spherically symmetric neutron stars, and we looked for a solution to this system that, of course, solved the initial condition of the problem, which are kind of complicated for this theory, but at the same time that allowed for solution with a vanishing scalar field at infinity so that we can retrieve GR at spatial infinity. The first main result of our paper was the study of the parameter space. Here I'm showing the specific case for an equational state, for an NPA1 equational state. It's not the only one that we consider. We also consider a Sly equational state. And in this case, we are focusing on a specific central energy density such that when studied in the GR case, this gives an ADM mass of 1.12 solar masses. So just to remind you, beta is the coupling parameter of the Ricci scalar and alpha is the coupling parameter of the Gauss-Bonnet. Let me explain you briefly what this plot is showing. So this white region is the region where the branch of GR solution is stable. So GR solutions are favored. So if we choose a point in the parameter space here, we will just receive GR. When this first black line is the threshold for spontaneous scalarization. So when we cross this threshold, what we have at a linear level is a tachyonic instability. So our system is affected by instability. And each time we cross a black line, we are increasing the node of solution, the node of solution that we can find. So in this light gray region, we have only 0 node solution, then we have 1 node solution and 0 node solutions, and so on. The important part of this plot are these two colored regions. These color regions are represents areas of the parameter space where we can find a scalarized solution to our full system. So we do not only have an instability at a linear level, we are also able to find solutions of the full system of equation. And in particular, the red region is for 0 node solution. The blue one is for 1 node solutions. We are not including higher node solution to not complicate further the plot. But already here we can see that the parameter space can be constrained from this analysis, especially if we look at this gray region. We can see that we know that this gray region GR is not stable, so there is an instability and scalarized solutions are preferred to the GR ones, but at the same time we are not able to find, the full system of equation does not have a solution, either because the initial conditions are not satisfied or because effectively we cannot find a solution that goes to 0 at infinity. So we already know points of the parameter space that belongs to these two regions need to be discarded. The second part of our paper focused on the study of the properties of the star, and in particular on the ADM mass and the scalar charge. And here I'm simply showing one plot to just give you an idea of what we did. And I'm showing the ratio between the two because thanks to observation from binary pulsars, we can constrain this in this formalism. This is a dimensionless quantity, so we know that we can constrain Q over M. And I'm not going into the details why this has to do with sensitivities. I have a slide if you want to elucidation on this. But here I'm showing a particularly straightforward case for this analysis. So this is a slide equation of state for a higher central energy density and for a positive beta, and we are varying the coupling parameters of the Gauss-Bonnet. And it's clear that so when alpha is rather small, let's say, this condition is satisfied. So this point of the parameter space, these choices of parameters are good, so for what we know. But at the same time, when we consider a second branch of solutions where alpha is quite big, it's clear that this condition is violated. So points of the parameter space with this alpha choice of parameters with this beta and this alpha cannot be considered. And of course, we did this analysis for different values of beta and different choices of equational state and central energy density. I'm just showing the clearer plot to understand what we did. So in summary, what we did was studied spontaneous scalarization for neutron stars for the first time for a theory that contained both the Gauss-Bonnet and the Ricci scalar couplings, which was never done before because so far people just consider or the Gauss-Bonnet theory or a Ricci scalar couplings. And we were able to put some preliminary constraints on the coupling parameters simply by consideration on the parameter space or on the properties of the neutron star. And of course, there are still many things to do. We could do a stability analysis of neutron stars. Yorgos this afternoon will talk about black hole stability for the same theory. One could also study well-posed initial value problems of such theory, which has not been done so far. And we can complicate further our space-time assumptions by adding rotation to our system. So yeah, there is still much to do, but this is what we have been done so far. So thank you.
Thank you very much. Does anyone have any questions for Giulia? There's one coming in there from Zachariah. Thank you for the talk. What about considering the coupling more general in function of phi? Phi is.
Sorry, let me see, because I don't see it. Can you repeat?
What about considering the coupling more general?
Oh, yeah.
Function?
Yeah, sure. We could complicate further the coupling function. So let me go back to the action. In principle, we could do, but the point is that for what regards the triggering of spontaneous scalarization, so at a linear level, the main term the terms that trigger spontaneous scalarization is a quadratic coupling. Of course, one could include higher powers of the coupling function, and usually this is people do so because higher, so like for example, including a phi to the fourth term can render the solution stable, more stable with respect to the just a quadratic coupling. We didn't do so, first of all, for simplicity, and because this is the action that we've been working so far in the other papers, but also because in the black hole papers, so we did a similar analysis for the case of black holes, and we showed that already including the Ricci scalar in the theory allowed for stability of black hole solutions. So it wasn't necessary to include higher powers of the scalar field. And so we are kind of expecting the same for neutron stars. Of course, one should do a stability analysis to consider this. But at the linear level, just a quadratic function is enough to trigger spontaneous scalarization.